Kia ora koutou katoa, everyone. Thank you, Chris, for the kind invitation. And it's really nice to be back and be here because I realized about 20 years ago, almost exactly 20 years ago, in a month or two, is when I actually had my PhD viva. So I'm just going to show you this photo, which is actually really difficult for me to look at because this I can see is someone who's pretending someone who she's not. And while I tried my best to be myself when I was here, I actually hid who I was. And actually, it's really nice to come back, and I thank the organising committee for letting me speak, because I can actually try and put my past behind me. So to introduce myself, so you all know who I am, I'm Professor J Eldridge, my pronouns are she, her. I'm obviously an astrophysicist, I use this slide a lot, so there's things in here that you already know about me. I'm the current head of department of physics at the University of Auckland, which is in New Zealand. So I don't think anyone has actually travelled further to be here than I have. 34 hours door to door, it was great fun. I study exploding binary stars while exploding the myth of a gender binary. In case you haven't realized already, I'm transgender. What that means is my gender does not align with the sex I was assigned at birth because I understand myself, after a few decades, a lot better than the doctor who looked at me for 5 seconds and went, boy, how wrong can you be? And it's really nice to come back to the IOA because I can actually see in the 2 decades since I did my PhD, I also came back as a postdoc and have been here on research and study leave, I can see how the work to be inclusive and make a diverse and equitable work environment has actually changed, right? You can see this for the posters they have around. You can see it with the wheelchair-accessible telescopes up on the lawn, and you can also see it with the anti-bullying posters in the bathroom. So you're all going like, are there? Obviously, you haven't been looking out, but it's really good to be back and have this opportunity to talk. And so yes, I work on stars, galaxies, and supernovae, and I'll be talking now about binaries. So binary stars, what are they? We've already had an excellent introduction by Abhishek, but this is a picture that I like from Mark Garlick, where you can see you've got the initially more massive, hotter star is evolving faster, so it transfers material because it fills its frost lobe onto a lower mass, cooler companion. And then some weird stuff happens. You maybe get an accretion disk, maybe you get spun up, but you get mass exchange. And with binaries, you've got to get away from the idea that it's just two stars orbiting around each other. It's when they interact and get in each other's way that all the fun stuff happens. And actually, when we teach undergraduate courses, we should not be teaching single star evolution as the default. We know for massive stars, 60 to 70% of all massive stars must have their evolution affected by binary interactions, which is actually quite worrying. So Abhishek just showed his version of the HR diagram, which we found out last night, thanks to Jerry Gilmore, that the Hertzsprung-Russell diagram, a lot of the work was actually done here in Cambridge, so it's nice to show this HR diagram. This is my version of Abhishek's plot. So in single stars are the black lines, and the colored lines are what you get from the 180-odd models that I have with the same initial mass, but with a different binary companion and a different period. They are different because these are from the Cambridge Stars Code, not from Maser, different metallicity, different other assumptions put in. But you can see it does look a little bit like a mess. But when you get used to it, you realize there's actually patterns. There's Roche-Lobe overflow, and there's merger products. And again, so the really key thing to remember about binary stars is we now have these helium stars that have always been hypothetical. We've already predicted and shown that they must be type 1bc progenitors, but now we know they exist. And look at their surface temperatures. They're close to 100,000 degrees Kelvin, which changes the ionizing output of the stars or the stellar population, which will change your H2 region emission lines. And we've shown with some work in other studies with a previous student that's important. So this is great. This is the models. You want to be able to use these to make model populations, then you can compare them to observations in the same way that Avishai has just done. So how do you take 250,000 stellar evolution models, detailed stellar evolution models, so they've taken minutes each to compute, and if you multiply all that together, it's something like several million minutes of CPU time, which is probably a few years. You have to take those stellar evolution models, combine them with your initial binary parameters, just as Abhishek just said, but you need to think about all the other things that you're including within your binary model. And then from using your models with your initial parameters, you can make your population predictions, things like number counts, delay time distribution for explosive events. But then you can go one further, which is actually what I'll talk about in a second, with making synthetic stellar spectra on top of your population, and you can work out what these things look like. And that's really important because, you know, when you go to observe a galaxy in a telescope, you take this thing called a spectra. You don't want to have to count the number of stars in there. You just want to compare that spectra straight to a model from a binary population synthesis code. So you can do this with BPass, and so this is where you get the intermission, right? This is the advertising break in between the talk. What is BPass? BPass is the binary population and spectral synthesis code, and at its heart, it's a group of people. It's actually me and Elizabeth Stanway, who were PhD students here. Me and Elizabeth have known each other since about the first or second week of our first year of undergraduate. So really, for students, be careful who you make friends with, because you may be stuck with them for quite some time. And when we finished our PhDs, we said, hey, we need to start a collaboration together to stay in contact. So that's where BPass came from, because Elizabeth was looking at high redshift galaxies, and I was looking at the supernova progenitors. And this is where BPass came out of. And now we've got this wonderful team of postdocs and students who are working on us, with us to actually try and improve our models. And of course, we've also got all these past students down here that have contributed to our work over the time. So to get away from the people and think about what physically, well, it's a computer code. It's a suite of computer codes, and there's nothing physical about it. You've got a custom version of the Cambridge stars code, which is still the same version that I used when I started coding up over there in the Caulfield wing in about 2003, 2004, but of course modified, and that's where we get our 250,000 stellar evolution models. And then behind that, on top of that, we have that population synthesis, where you take all your models, you try and make a population out of them. And then the really fun thing is you take your models as close as you can to observations, right? You don't want to take the observations close to your models because you have to make assumptions. But you know everything about your model, and if you can take it as close to observation, that's great. And so we do have, within the code, we have our electromagnetic spectral synthesis. So, you know, if you're a 20th century astronomer still using light, you can do that. If you've come into the 21st century and you're using gravitational waves, we've now started doing the population spectral synthesis for gravitational waves, and that's really exciting. What does this mean? We've got all these observations we can constrain the same models with. Oops, sorry, gone too far. And that's really, really important. And the good news is we've now got a Python package that you can use to actually understand, to easily use the BPass results, and it's called Hoki. Hoki is a Maori word from New Zealand for fish, and the idea is you can go fishing in BPass data to compare it to your observations. Okay, it's sad, I know, but you know, you've got to find amusement in life somehow. So this is the one both slides. So this is all the work we've done, or I've been involved with, using version 2 to compare to observations. So there's a lot of transients work here, high redshift galaxies, massive star populations, X-ray binaries. The importance of this is you can have some confidence in the BPass results, because while we may not be absolutely correct, we're at least on the right lines, and we at least do a pretty good job without comparison to observations. And there's clearly things to improve. You can see that from Jim's talk and from Abhishai's talk, but it's along the right lines. The one thing we haven't done is many low mass star comparisons, and I'll get to that in a second. But I really wanted to talk about how do you compare BPass to other codes. So there's actually quite a lot of binary population synthesis codes out there. Everything in white on this plot, which is actually by Giuliano Iluro, is a population synthesis code. How do you pick between them, right? Well, if you actually want to do spectral synthesis, you have to choose BPass, because that's one of the very few that actually do it. But actually, you can see down here in stars, down here in the bottom left-hand corner, has given rise to this huge island itself, with these being the rapid population synthesis codes based on Jared Hurley's work. And of course, BPass is using the same stellar evolution code, but we're making detailed evolution models. So let's get on to the plot that Chiaki didn't show, that I was expecting her to. She showed a different plot. But Chiaki did, in that paper she mentioned, an amazing job. She got 5 of the population synthesis people to share results, to do a direct comparison. We hate doing this, because none of us want to be wrong, right? And you can see clearly that here, where we're matching the type 1a supernova rate to the core collapse supernova rate, which is giving you the oxygen and the iron, they're mostly the same. There are some subtle differences, but they're not going to make me lose sleep at night that they're different, right? Because there's enough uncertainties in both the models and probably the galactic chemical evolution model. But it's really exciting to see that we actually get the same answer. But when we look at the binary neutron star merger rates, this is actually really scary, right? Because we're all very different. There is a piece of physics, what we're assuming in the binary population synthesis, or sorry, the binary evolution code, that is giving us different answers to do with the delay time distribution. And with the delay time distribution with BPass, we've actually found we've got the broadest one. I checked it just before my talk. I checked the paper, and it's interesting that that's actually what we're measuring. You need a nice broad delay time distribution to produce enough binary neutron star mergers. And here there's still enough space for the rotational hypernovae to have an addition as well, which would be interesting to redo this, but having the rates from that for the different codes too. So there's good and bad here, right? So there is good, that we're similar, but there's differences. And actually, by comparing the codes, which is actually quite scary, but something we should do, we can learn a lot more. So what else can we do with binary neutron star mergers? And so I'm just going to cover quickly the work I'm most proud of in the last few years, which is actually studying this thing. Right? I should have actually just taken the number off and see if anyone can actually guess what galaxy it was. But it's the host galaxy is GW17017. Now, when it went off, everyone went and analyzed the host galaxy to get the star formation history. Because you can actually get the star formation history, you can work out how old the progenitor was. And this is the one that was done by Joe Lyman on a paper led by Andrew Levan. The problem is, this is with single-star spectral synthesis models. Now, correct me if I'm wrong, but a binary neutron star merger comes from a binary star. So you should actually use a binary spectral synthesis model in this galaxy, because there's got to be other binaries. The Royal Society of New Zealand agreed with me, gave me $1 million New Zealand dollars, not real dollars, not American dollars, just New Zealand dollars, to write a spectral synthesis fitting code. And this is our results. And this was work led by Heloise Stavance, who's now in Oxford, working with Stephen Smart. And you can see we get very different star formation histories. In the Levan paper, the 1 billion-year-old burst is actually much stronger, whereas we find there is a burst there at 1 billion years old, but it's much, much smaller. The progenitor was much more likely to be 10 billion years old. That's a significant change in your trying to understand the progenitor. Okay, so Jan, now you've done this fit where you've got the electromagnetic light, but this is a gravitational wave event. With the same models who made the spectra, we can go and look after the binary neutron star mergers and actually constrain the initial parameters and the evolutionary history of the progenitor, because we know that we've got to find one that's about 10 billion years old. Although you use all the star formation history, you don't say ignore the lower mass. But you can say that it's much more likely to be a 10 billion year old progenitor, and that's really exciting. Thanks, Chris. And so we actually know where this all maps together. And why am I so proud of this? Because it's the first time one set of models have been compared to both electromagnetic and gravitational wave information from a single event. And okay, one event's not much, but can you imagine what happens when we get 5 or 6 of these? And we can start building a delay time distribution for these events, which will be really exciting, and actually start constraining models. Okay, in my last 30 seconds or so. Chris got it right. What's really going to be excited about is LISA. This is going to be fantastic and actually change the game. If it flies, hopefully, fingers crossed. This is the white dwarf binary population that LISA is going to see, predicted by BPAS in blue and a BSC variant from Astrid-Lamberts in red. You can immediately see that BPAS predicts many fewer binary white dwarfs. If you're a supermassive binary black hole person, you'll love this, because you're going to have no galactic foreground and you'll be able to see lots and lots of merging supermassive black holes. If you're a stellar population person, you're going, what has Jan done with all her white dwarfs? Why does this difference come from? We're still trying to work this out. Just because I haven't got any time, that if you're above that red line in the binary system, your initially less massive star is now the more massive white dwarf. So you flip the mass ratio because of the stable mass transfer. And so if BPAS, most of the white dwarfs in the LISA band have had stable mass transfer. And actually, this is the big thing that we need to work on with binary populations, is to constrain how stable mass transfer is. And that's the big mystery that we've got. So I'll leave you with my conclusions, or final thoughts, really, which is a key takeaway is if you're ignoring binaries in most of your analysis of stellar populations, you're not getting the full answer. You might be missing something really obvious. We've made it as easy as possible for you to use binary models, and we can help you, but nobody likes emailing or talking to other people, so you can just download it and you don't have to use it yourself. But we really, as binary population and binary models, need to start working together, because that's where we can see the differences in our code and understand which physics is actually reasonable. Anyway, so thank you very much for listening, and I'll answer any questions.